In this video, we'll be exploring surface area and volume. Surface area and volume are measurement concepts about 3D objects. 3D stands for three dimensions, and objects in our world can be measured according to their length, width, and height. This particular 3D object is called a rectangular prism. We'll define what that means in a few moments, but first, let's apply a grid to this prism so we can think about the different ways we can measure it. The volume of a 3D object means the amount of space the object occupies. It is measured in cubic units. The surface area of an object means how many square units it takes to cover the object. Imagine it's like painting the object a different color. Let's first explore surface area and begin with some prior knowledge we need before going further. Here are some familiar shapes, and they may form part of the surface of a 3D solid, so we need to know how to determine the area of each. A rectangle has a base and a height, and its area is calculated by multiplying the base by the height. A triangle also has a base and a height. A height is a distance from one point to the other side, meeting it at a right angle. A triangle has half the area of a rectangle with the same base and height, so its area is calculated by base times height divided by 2. A circle has a radius, which is the distance from the center of the circle. Its area is calculated using pi times r squared. Pi is approximately equal to 3.14, but it is better for students to use the pi value that is stored on their scientific calculator. There's something to note about the height of a triangle, and that is that if the triangle is obtuse, its height is still measured at right angles to its opposite side. A circle has another measure that we need to know. The distance around a circle is called the circumference. It is calculated using 2 times pi times r, or simply 2 pi r. As mentioned before, an object like this is called a prism. A prism is defined as a 3D object with two opposite faces that are parallel and congruent. To see the meaning of this definition, these are two opposite faces. A face is a flat surface on an object. The faces are parallel because if they were to be extended, they would never meet. We can also see that these faces are congruent, meaning that they have the same size and same shape. Prisms are named by the shape of their base. The base of this prism is a rectangle, so it is called a rectangular prism. The base of this prism is a triangle, so it is called a triangular prism. This prism has a square base, so we could call it a square prism, but notice that all 6 faces are squares, so we give it a special name, a cube. Another prism with a special name is one which has a circle for its base. It is called a cylinder. We are now ready to explore surface area. Recall that the surface area of an object means how many squares it takes to cover the object. Here is a different view to help us see all the faces of a prism more clearly. There is a left face and a right face, a front face and a back face, a top face, and a bottom face. So in total, there are 6 faces. The surface area will be the total area of these 6 faces. To determine the area of each face, we need to have dimensions, so we could figure out how many square units are on each face. From the grid, we can see that the width is 4 units, the length is 6 units, and the height is 3 units. You have enough information now to determine the total surface area of the prism. Before we explore together, take some time to think about how you would calculate it. Let's examine each face separately. The left face is 3 units by 4 units, so its area is 12 units. The right face is congruent, so its area is also 12. The front face is 6 by 3, so its area is 18. The back face is congruent, so its area is also 18. The top face is 4 by 6, so its area is 24. The bottom face is congruent, so its area is also 24. So for the prism as a whole, the surface area is the sum of these areas, which is 108. It is important to include units with our measurements. Area is measured in square units. Because opposite faces are congruent, notice how we can group the areas of 3 faces together. These are 2 areas of 12, 2 areas of 18, and 2 areas of 24. So a more efficient way to determine the total surface area is to add just 3 areas together, then double the sum. One of the more challenging aspects of calculating surface area is to make sure that all faces have been considered. If we unfold this prism, we can see all 6 faces at once. This 2D representation is called a net. Returning to our previous prism, we can rearrange the 6 faces to show what the net would look like. So, when solving a surface area problem, it is very helpful to sketch a net first. Let's take a moment to see visually the connection between a 3D object and its net as we adjust the dimensions. Next, let's generalize how to calculate the surface area of a rectangular prism. We can use labels to match up faces of the 3D object with its area on the net. There are 3 faces that we cannot see in the 3D object, but we can still label them on the net. The total surface area is the sum of the areas of the faces. But as we saw earlier, all we really need for a rectangular prism is to consider the 3 faces we can see because the other 3 areas are congruent to these. Thus, we can calculate the total surface area of a rectangular prism by determining the area of the 3 surfaces we see, then doubling that sum. But what if the 3D object had a curved surface, such as with a cylinder? What would the net of a cylinder look like? Think about what shapes you would get when you unfold a cylinder. Observe what results when a cylinder is unfolded. Before we take a closer look at that again, let's label some measurements on the cylinder. As with a prism, a cylinder has a height. Its base is a circle, so it has a radius and a circumference. Watch the circumference closely as we unfold the cylinder once more. Notice that the curved surface of the cylinder becomes a rectangle when it's unfolded. The circumference of the circle is one dimension of the rectangle, and the height of the cylinder is the other. The top and bottom of the cylinders are circles. The area of each circle is pi r squared, and the area of the rectangle, then, is 2 pi r times h, or 2 pi r h. So the total surface area of the cylinder is 2 pi r squared plus 2 pi r h. Now let's apply all that we have learned to some sample questions from the textbook. Calculate the surface area of this ramp in the shape of a right triangular prism. Give your answer to the nearest tenth of a square meter. As we learned, to determine a surface area, it helps to sketch a net first. What would the net of this prism look like? The parallel faces of a triangular prism are triangles, so let's look at those first. As we draw the net, we also label the lengths of the sides. The other three faces are rectangles. First, there is the bottom. Then the back. Then the top. The area of one of the triangles is 1.61. The other triangle is congruent, so its area is also 1.61. The area of the bottom rectangle of the prism is 1.61. The area of the back rectangle of the prism is 0.98. And finally, the area of the top rectangle of the prism is 1.89. So the total surface area is the sum of the areas of the faces, which is 7.7. And we need to include the unit meters squared. Let's read through this next problem. Anu wants to recover the cylindrical stool in his bedroom. How much material does he need if there is no overlap and he does not cover the bottom of the stool? Let's visualize the surfaces that Anu wants to cover with material. There is the curved surface and the top circle. Note that it says that he does not cover the bottom. So although the formula for the surface area of the cylinder has 2 pi r squareds, in this context we only count one of them. To evaluate this formula, we first need to know r, which is the radius. We are given that the diameter is 42 centimeters, and the radius is half of that. So r equals 21 centimeters. Next, we need to know h, which is the height of the cylinder, and we can see that it is 32 centimeters. Substitute 21 for r and 32 for h and carry out the calculations. We calculated that Anu needs 5,607.7 centimeters squared of material to cover his bedroom stool. Next, we will explore volume. Recall that volume tells us how many cubic units an object occupies. Recall also the dimensions of this prism. With this information, can you figure out how many cubes in total make up this prism? Let's rebuild this prism to see how it is made up of cubes. First, it has a width of 4 units. So we begin with 4 cubes. Next, it has a length of 6 units, so we can complete the bottom face. So in total, the bottom face has 6 rows of 4, which makes 24 cubes. Next, it has a height of 3 units, so we have 3 layers of the bottom face. Each layer has 24 units, and we have 3 groups of them for a total of 72 cubic units. Notice that once we had the area of the bottom layer, or the base, all we had to do was multiply by the height. This is an important general idea for determining the volume of any prism. We begin with the base and determine its area. We can label it A of base for short. That base is then extended through the height, and this completes the prism. So the total volume can be calculated by first figuring out the area of the base and then multiplying by the height. Here is a shorter way to write the general formula for the volume of a prism. Notice that we can apply this formula no matter what kind of base the prism has. If we know the area of the base, we can multiply by the height, and thus determine the volume of each prism. Now let's apply all we have learned about volume to some sample questions from the textbook. Determine the volume of this right triangular prism. We have our general formula for the volume of a prism. See if you can use this formula to calculate the volume. First, we need to consider the area of the base. The base of this prism is a triangle, so its area is base times height divided by 2. Note that the h in this formula refers to the height of the triangle, not the height of the prism. The base of this triangle is 8.1, and its height is 2.2. Substituting into the formula shows that the area of the triangle, which is the base of the prism, is 8.91. The height of the prism is 15. So substituting into the volume formula shows that the volume of the prism is 133.65 cubic meters. In this next problem, we are given that two cylinders have the same volume. The first cylinder has a diameter of 10 centimeters and a height of 30 centimeters. The second cylinder has a diameter of 8 centimeters. We are asked to find the height of the second cylinder to the nearest tenth of a centimeter. Before we move on to calculate this unknown height, think for a moment, what is a reasonable estimate for the height of the second cylinder? Is it more than 10 or less? Is it much different or close? Let's organize the given information into two columns and then draw a sketch of the first cylinder. It has a diameter of 10 centimeters and a height of 30 centimeters, so the cylinder is tall and narrow. The next cylinder has the same volume but a narrower diameter, so it must be much taller. For both cylinders, we can use the general formula for the volume of a prism. In this case, our prisms are cylinders, so the bases are circles, meaning that the area of each base is pi r squared. The first cylinder has a diameter of 10 centimeters, so its radius is 5 centimeters. Substituting into our first formula shows that the volume of the first cylinder is approximately 2,356.19. The second cylinder has a diameter of 8 centimeters, so its radius is 4 centimeters. This time, when we substitute in the formula, we get an algebraic expression, 50.27 times h. We were given that the two volumes are the same, so we can make these two expressions equal. To solve this equation, we need to isolate h, So let's divide the left side by 50 decimal 27. To keep the equation balanced, we also need to divide the right side by the same amount. This shows that h is approximately 46 decimal 9 centimeters. An interesting alternative approach to this problem is to consider how the cylinders compare to each other. Their radii have a ratio of 5 to 4, but the radii are squared to get the area of the circles. If we multiply this result by the height of the first cylinder, we get the height of the second cylinder. For our final homework problem, we are given a wooden block formed in the shape below, and we need to determine the volume of the block. An object like this can be seen as made up of many objects, so it is called a composite solid. To determine its volume, we need to divide it up into prisms that we know we can get the volume of. Take a moment and think about how you would divide up this prism. One way to divide up this composite solid is to split it up vertically. But a more interesting and efficient way is to consider what has been removed. So we can consider the whole solid and what has been removed. If we label these two volumes as V1 and V2, we can express the volume of the composite solid as V1 minus V2. Using our general formula for volume on V1, from its dimensions, we can multiply the area of its base, 10 by 16, by a height of 10. For V2, from its dimensions, we determined the volume by multiplying 5 by 6 by 10. Evaluating both these volumes, we get that the total volume of the composite solid is 1,300 cubic centimeters. An alternative strategy we could have used would be to determine the composite area of the base and multiply that by the height of the prism. A common mistake that students make in this unit is to confuse whether they are calculating surface area or volume. For example, with a cylinder, we have a formula for its surface area and a formula for its volume, but which do we use in a particular context? The important thing to think about is what the context is asking them to determine. Use surface area when it is about the surface of the cylinder, like when we covered a new stool with material. Another mistake that gets made is about units. Surface area uses square units, and notice in the formula that each term involves the multiplication of two variable values. Volume gets used when it is about how much stuff the cylinder is made of or how much the cylinder contains. Note as well that volume uses cubic units, and notice in the formula that the term involves the multiplication of three variable values. Speaking of surface area versus volume, let's go back to our original prism and consider an interesting problem. We figured out that the surface area of this prism was 108 units squared, and the volume was 72 cubic units. But what if we rearrange the 72 cubes into this shape? It still has the same volume, but what about its surface area? How does the surface area of this new prism compare to that of the first prism? Is it the same? Is it more? Is it less? It turns out that the surface area is 132 square units, which is more than the original prism. This makes me wonder what other surface areas we could get by rearranging the 72 cubes into a new prism, and especially which of those prisms would have the greatest surface area. I'll leave that with you as a problem to think about. This video addresses several learning standards in the Mathematics 8 curriculum. First of all, this big idea is addressed throughout the video. We described, measured, and compared the surface area and volume of different 3D objects. In content, we looked at surface area and volume of regular solids, including triangular and other prisms and cylinders. Several curricular competencies may emerge as your child learns and applies the content from this chapter. We saw that there were multiple strategies we could use when determining the surface area or volume. Visualization was very important to figure out what the net of a 3D object would look like, and also to determine what the base was of a prism. Drawing sketches was a helpful representation to organize our information so we could calculate a surface area or volume. Finally, we not only explored surface area and volume separately, but in our final problem, how they connect together.